Okay. Hi, I'm Tom Scholl with AT&T, and I'll probably be the last presentation before lunch. So if people walk out, I don't know if it's because they're leaving or they just don't like it. So anyhow, this presentation is going to be about rapid convergence and IP networks, and basically just get things out of the way. In terms of convergence, we're not talking about Twitter, Facebook, LinkedIn, different applications coming together. It's nothing like that. We're specifically talking about convergence as it relates to how IP networks route around failures and network changes. And basically, we're just talking about in the intra-domain, so within your network, not talking about external of what happens when you're doing EBGP pairing to all different autonomous systems. This is just really within inside your own domain, your own house. So, what's the problem you're really trying to solve when dealing with a convergence? And basically, events occur within IP networks that can typically result in traffic being dropped. And when you have traffic being dropped, there's typically the result of, it could be due to congestion, it could be a forwarding error, such as a link has gone down, traffic's getting black-holed, it could be some sort of forwarding issue on your actual equipment where traffic is not being written to the right line card and then it drops. And finally, the last option is TTL expiration, which is pretty much a good sign if you are experiencing large amounts of TTL expiration that there's actually a routing loop at play. That or it's actually just trace route. But generally, TTLs are a good sign to point that something's actually looping back and forth. And basically the whole idea is, well, the convergence is really the time that we can recover from some sort of event like this. And why is it why we're bringing this about IP networks and rapid convergence is that frequently a lot of people compare SONET and other types of transport services to IP, and the notion, or the rumors say, or different people say that you can't get IP networks to actually go that fast. They can't reconverge that fast. It's best effort, maybe a few seconds. And the reality is you can actually do some pretty interesting things within your own autonomous system and getting things to route around failures. It is feasible, and so the rest of the presentation covers pretty much what are your options in that regard if you actually do try to aim to do it, and what kind of things you'll run into. So really, who are the end people who actually do care about rapid convergence? And the specific applications, voice over IP, IP-based call centers. Some of them are really aggressive in terms of what happens when they drop a few packets for several seconds. They'll terminate a call. There's some phone handsets that'll actually, soft reboot if they don't talk to their central device that they're communicating with. Another one is in the video space, and just IPTV and other types of video that they're very sensitive to dropping any kind of frames. Depending on the codecs that are used. Video is another sensitive one. And finally, another one would be cellular and mobile networks, where you have like SIGTRAN signaling, you have voice traffic routing, and some mobile networks, they've gone from having from mobile voice data going over ATM networks that they've actually, some places actually replaced it with IP MPLS networks, and they're running pseudo wires to keep part of that ATM infrastructure still alive. And in those cases, they're still running the older architectures on newer IP networks, but they still have to meet that level of reliability. And basically, the other one is pretty much anybody who's been buying legacy transport services who is accustomed to a particular type of behavior, and maybe they're transitioning onto a layer 3 VPN, and they have the expectation that, hey, it should just be fast as what I had before. So what are the kind of application targets that, if you're a service provider, whatever you're building, what would you have to support from your individual customers, right? And what it comes down to is each application has its own, amount of threshold of what it can handle before things degrade or break. And one common thing that does seem to come up quite a bit is that there's a 50 millisecond goal or golden standard that everyone tries to build to, or at least talk about, or at least demand as a requirement, right? And they say, we have to have 50 milliseconds. That's SONET, or in some cases even sub-second are okay for some people. But 50 milliseconds is really, the name comes up quite a bit. And where did it really come from? Well, the telco world, not a surprise. And it is really, basically a standard that was set for the heal time on SONET rings. But the thing was, there was really no specific application, from the end user space that said, I really need 50 milliseconds. There was nothing out there. It was pretty much a standard that was set, and everyone's been trying to meet it. So, next slide is, well, going back to the convergence topic. Well, now that we know there's a 50 millisecond thing that some people are trying to meet, some people will try to get at least close to. Well, when it comes back to convergence, what kind of things are we even dealing with in the first place? So generally, link and node failures on a router in your network, that's going to cause something to happen. The other one is a simple IGP cost change, right? You know, IGP cost change, you think, oh, we'll just increase it, take the circuit out of service. Doesn't work like that. Just increasing the cost alone will trickle across the network, and you actually will probably see some amount of a micro loop for some period of time. So that doesn't always work the best. And, you know, it has different operations occur after you do something like this. So, you know, the link state advertisements have to be advertised. SPF, the shortest path first tree, has to be rebuilt. And basically the result of that is that you have to, you know, program any changes in the actual forwarding plane at that point. And, you know, this whole operation can take a little while, right? And a little while could vary from anywhere from, you know, milliseconds to hundreds of milliseconds to even seconds in a few cases, depending on the hardware, how busy that hardware is at that given moment. It's totally variable. And, you know, on top of that, whenever you do make some sort of change in your IGP within the network, every router is going to run SPF, but, you know, every router is doing different functions. Somebody might be processing BGP, somebody's SNMP walking another box. You know, SPF is going to run, and its runtime is going to be different on every box throughout the network. So it's a bit of an autonomous action on each router. So, you know, what kind of happens in a IGB convergence type event? First of all, you have to detect it, right? And, you know, that's hard enough in some cases because depending on the media that you have, you know, if you have layer 3 adjacency protocols set up, you have dead timers that you can set and you can crank down to be lower. But basically, you know, the first thing, you know, you want to talk about convergence, you have to detect it. Once you detect it, then you certainly need to advertise the topology changes within the network, right? So tell everybody else what happened, and then you have to take all those updates, you have to push down on the individual interfaces and package it out. Then once everybody does hear about the event, they have to recalculate SPF. Then once again, you know, update the local RIB in the router, and then finally update the forwarding plane, which is actually what, you know, makes the difference when it comes to where the traffic is going. You know, so if you're going to embark on this path of, you know, want to do something better than just the default config, you know, defaults aren't going to cut it, right? You're going to have to tweak a few knobs. When vendors ship boxes, you know, new code updates, they don't put a lot of convergence changes in the default command lines, right? Because there's somebody who's probably running with the defaults who's happy with that, and they don't want to have, you know, upgrade code and all of a sudden the behaviors change. So typically, there's going to be a few knobs that you're going to have to tweak, and, you know, some of those are going to vary from playing with SPF intervals, throttle timers, flooding controls, some commands that are going to be related towards the fib and programming, some things within the RIB itself. And then most of all, you're going to have to worry about you know, failure detection. And there's a few things there. You can worry about layer 2 keep alives. You could do things with lowered IGP timers, although then that's one way. Another way, you know, certainly BFD works as well if you can support it and scale it pretty well. But on top of defaults, you still need to converge really fast, right? And so far up to this point, we talked about, you know, recalculation has to happen, right? But if you really want to be fast and you want to, you know, get it to be somewhat sub-second, you're going to have to rely on something that's a little bit better when interacting with the fib as to getting traffic routing on the right path. You know, with the right knobs, even with just plain vanilla IGP, depending on how large, you know, your internal routing table is, you can still get within the 100 milliseconds range. I mean, that's certainly feasible. But if you really want to, if you have to, for whatever reason, you know, go for a lower value, there's really two options that really come about, and that's basically IP fast reroute and MPLS TE fast reroute. So just going to have another slide here, just kind of going into IP fast reroute, and then you know, the rest of the talk kind of goes into some of the dilemmas associated with TE. But with IP fast reroute, basically one really nice thing about it is it doesn't require MPLS. So if you're not committed to using labels and you don't want to use labels, or you don't want to continue to use them, you know, this is a possible viable option for you. It basically builds to, you know, some of the implementations that are out there. I believe XR has it today in ISIS, and, you know, I think that'll eventually go to OSPF. And I'm not sure if any other vendors actually support it today, but basically it does provide a rapid way for the IGP to actually, you know, have the alternate routes already in place. You know, there are some issues with SRLG, shared risk link groups, and how do you basically instruct the router to know what those are within your IGP. And we'll get into that. The issues are related to SRLGs a little bit later. You know, it still has a place, though, even in MPLS networks, where based upon the topology, it could work out really well. Specifically, if you look at leaf nodes, edge routers, which basically have, you know, two uplinks. It's a very simple topology. IPFR could work here within MPLS networks, or even in just regular IP networks as well. You know, the only drawback is you kind of lose the ability to do any kind of explicit path routing, but that's because you're not, you know, clearly doing anything with labels. So, I mean, it's got its own trade-offs, but it's a little bit not as heavy-handed as committing yourself to RSVP-TE. The other way is with MPLS-TE fast reroute, which has been out for quite a while, and there's really two ways you can kind of do this, right? You can basically have a head end of a router when you build an LSP somewhere. You could basically have a secondary LSP that's standing by and ready to go. So as soon as it gets a path error message, it can then switch over to your second path, right? And that second path can be explicitly created, or you could have it defined, or some routers implementations will actually go off and try to build the second LSP from a diverse path from what was originally created. The other option is that you could do it on a per link by link or facility-based bypass LSP, which lets you protect individual tunnels as you go hop by hop through the network, or individual links as you go across the network. And the idea is, the FIB is pre-programmed with instructions required to actually, put traffic into that bypass LSP. Doesn't have any, requires any kind of SPF or rail calculation when you do have a failure. It simply knows there's a failure. Okay, we're imposing this label for right now, and then we notify everybody who had a tunnel through this box, and tell them that they have to re-optimize at that point. There is some suboptimal routing, obviously, with doing TEFR, because you're taking traffic that's on a path that's typically potentially shorter, and now you could be putting it on a potentially longer path for some period of time. The other problem, if you're going to go down the route of doing anything with TEFR, is you have to build these backup tunnels, and some of the drama associated with that is that how do you know what's actually diverse, right? You need to make sure that the link that you intend to protect is taking a path that doesn't ride anywhere on the same link, right? Because that would obviously, they both go down at the same time, and then nothing's fast at that point. So if you're protecting a Chicago to New York City link, well, the bypass probably should not run through Cleveland if it's on the same facility or conduit or same fiber system. The problem with this is trying to figure out what the diversity is in the network is not always an easy task. The problem with is having the visibility into the layer 1 network and knowing where actually things route. If you can get that information, it's definitely great to have, but how do you know it hasn't changed on you? Things happen, things change, they put you on the same path as what you thought your backup was. And if you don't own your facilities, you obviously have to get that from somebody else. If you do, that's certainly good, but even then you still have to parse through the data. And depending on what you could do, if you are lucky enough that you can get reliable DLR, circuit layout requests, you can at least try to, put that information in some sort of database or somewhere locally where when you go to actually build your backup tunnels, which, is a somewhat painful process, you'll have to actually spell out all the individual hops, or at least the hops you want to stay away from. And trying to do that manually, by hand is not a very easy task or a fun task, depending on how many tunnels you have to build. There was once, something in, I think in IGP and both OSPF and ISIS had the capability of where you can actually attach a specific SRLG identifier on individual links, which would kind of be a nice thing to use in this case. And then you could tell the tunnels, hey, you're protecting this link, stay away from these SRLGs. But I don't think it's been used in any recent code. I don't think it's in XR, and I'm pretty sure it's not in Junos at this time. And then the other part of this is, if you're going to go on the path of our, bypass LSPs, do you even have enough bandwidth on the backup path, right? Building capacity, just to run the network day by day is somewhat difficult. Now you want to do, bypass LSPs. Are you actually going to have the bandwidth in place there? Or otherwise, you're just going to be dropping packets, and what's the point of doing it anyways in the first place? And then on top of that, do you have any latency limitations, right? If you're punting people on a backup path, is it going on a longer path? Do you have SLA agreements with your customers that they're going to say, oh, well, we saw this bump up for however long till you got them off the backup path? How long do you want to re-optimize your LSPs? So you have to think about, what other things are you going to impact by just doing this? On top of that, just to figure out even where LSPs go, it's a bit complex. Modeling tools are helpful. There's a lot of vendors out there that have things that can, suck down the configs of every router in the network. They can build a topology. You can feed it traffic demands, and they can actually do a lot of the legwork for you, which are pretty helpful. And they exist for regular IPv4 or regular IP networks as well, but they certainly have some of the intelligence to do things with labels. One thing to note, too, is with the make before break, well, not even just really a make before break thing, but with TEs, when you're moving traffic from one LSP to another, you could definitely run into some reordering issue because you're taking the packets, you're putting on a longer path, and then you could bring it back to the shorter path again. So that's certainly a possibility of happening in the network. TE aside, there's still always going to be bottlenecks that are really beyond your control. One thing that you're going to run into is just on the routers that you're running, programming the FIB, trying to do it fast, having lots of things going on. Whenever there is a link failure, there's a lot of lot of things typically going on in a router. You're running SPF, you're sending updates to line cards. If you have multiple protocols at play, so let's say you're doing RSVTE, you're doing LDP, you're going to have contention for putting updates on the same line card. It gets pretty difficult, and maybe things can grow to be too complex at that point. The other thing was attempting to detect failures as fast as possible. There's a lot of timers that are associated with interfaces. When the link goes down, there's delay timers on when the link goes down, when it goes up. Do you need to lower some of those at the risk of potentially dropping an interface at what could be a minor at layer 1 flap? There's 802.3AH, the CFM stuff, which basically lets you work at layer 2 and essentially keep lives there. And then there's of course BFD, which is basically datagrams going back and forth that are typically bootstrapped to like a layer 3 IGP adjacency protocol, or layer 2 ISIS OSPF, to actually bring down the adjacency in the event of a failure. So can IP networks deliver sonic convergence speed? Well, pretty much. It is feasible that it can be done if all the right pieces are in place. And do you need to do this? So that's kind of another story. I mean, what are you really building for? And plus, on top of it, it's kind of up to the operator if you want to do a combination of these protocols, right? So there's IPFR, or do you want to use a combination of both, where you IPFR on the edge, MPLS in the core, where you can have more complex, backup tunnels that have to be created, or on the edge, it's pretty simple. Uplink fails, you move traffic to the other, so on. Pretty easy in that case. The other part is, even if you're going to go embark on this process of, we want to do rapid convergence for whatever particular user application, be it valid or not, who's actually counting, right? Who's actually out there saying, it wasn't 50 milliseconds, it was, 120 milliseconds? Who's actually watching the network to even provide statistics on this, right? Once if somebody makes a claim against SLA, how are you actually going to, prove it, right? You can log into the routers and say, we've got this syslog that says it moved to this LSP, so it must be true. But once again, the control plane on a router doesn't always match up what happens to the forwarding plane. So if you're, want to at least find out what the network is performing at, and a lot of people sometimes just don't even know, right? They log in the routers, they say, well, the SPF timer took 384 milliseconds, so padded a bit with a few extra numbers. We think that's what convergence should be. Certainly if you're going to go, you want to try to aim for some kind of low value. You definitely need to have the systems in there, and they need to be probing each other at very low intervals, and it should be reportable and somewhat readable to where it's actually useful to folks. And then the other thing is, if you are going to do this, right, and maybe it's a specific 1 or 2 or 3 customers that are requiring this, you need to at least question, are you going to do this for every single customer in your network, or are you just going to do it for a few? And if you do it for everybody, then everybody gets the benefit of it, but you're going to have to go through the pain of making sure that bandwidth is there. Or if you're going to do it for specific users and applications, how are you going to spread that across in your network, right? If it's one IGP, you're doing IPFR, everybody's going to get the same treatment. If you're doing TEFR, well, then you're going to have to jump in the boat of, okay, well, some people get this EXP value, but if they want FR service, then they get this other EXP value, and then they have to go on this different set of tunnels, and the complexity certainly goes up at that point. So you really got to focus on what you're trying to build for if you really want to go towards aiming for some of these lower values. Final slide here is just really how can you, if you do have some kind of desire to do, basically go from defaults to something playing with knobs a bit more. I just put some simple, little bullets here on some things to start looking, and definitely search online more about these commands in iOS as well as in Junos for things you could do to try to at least very basic improve some convergence. And some of them, your interface carrier delays, the amount of time it takes from an interface to transition to a downstate, right? There's in different implementations, there's actually 1 to 2 second hold on that. There's a lot of things, in Cisco you've got Ceph, and there's a lot of knobs that are related to how Ceph is handled, timers, how long it takes to push out changes to individual line cards that are certainly configurable. Your mileage may vary. Once again, in the IGP, there's plenty of knobs there as well as in terms of SPF throttling. By default, the initial SPF is 5 seconds. Is that something you want to be waiting for, or do you want to drop that a bit lower? There's process max time. How long should a process wait before going? I think before it should self-suspend, and IP routing per interface, which allows, I think, a linkage between the route, a link down and directly to talking to a routing protocol locally. And then on the Juniper side, next hop in direction, which is in a default setting, as well as playing with some of the SPF timers as well. So there's just some cheat sheet of ideas. You know, if you wanted to look into this, there's a lot of things out there. There's a few Wikipedia wiki pages out there that have some tips on things you could do. And of course, it varies on different platforms as well. So 7600s, GSRs, totally different. So definitely worth research if you want to have a place to start. That would be the place to go. But you know, you definitely have to ask yourself when you're building a network. You know, what are you really trying to go? You know, what is your target? Is it one specific customer who wants this? And you know, it really has you know, an effect across your whole network, because if you're just building towards one specific target, you know, it's going to make things a bit more complex. And you know, you have other customers you have to serve as well. So it's definitely a lot to think about. So that's it. So I don't know if there's any questions.
Hey, Tom. No question, but I know where the 50 milliseconds comes from if you want to know.
GR253?
There's nothing in GR253 that declares 50 milliseconds for sonnet switching. It comes from the old data storage networks of the old days. Think like EMC time frame. They require 50 millisecond switchover. How it worked its way into the telephony world, I have no idea.
Thank you.
But 200 is the magic number, I think.
All right.
Anton Capella, Voxel.net. So, Mr. Scholl, thank you for the talk. Did you get the chance to compare and contrast the affected differences at scale, like with UDLD versus BFD versus the IGP abilities? And if you can't even share that, like, what was the result?
I haven't played with UDLD, but I mean, in the past, you know, done some work with BFD. And what was the other one? I didn't.
Just IGP stuff. Like, in practice, did you get any good data out of this? The work you did leading up to this Prezo?
In the past, I mean, you know, past experimentations, I mean, it was just pretty much, IGB stuff is, if you're running small scale routing, you know, not a lot of prefixes, not a lot of adjacencies, the box isn't too busy, you know, you can crank down the IGB timers pretty well and you know, do fine. But otherwise, you know, that doesn't work for everybody. And BFD works out, but then BFD has its own scaling limitations. So it's definitely, you know, they certainly work. It's just, it depends what box you're using. How loaded is it, and how big is your network?
Thank you.
One more quick question. So I'm assuming you did this for our, I'll call them our legacy vanilla type IP cores. Have you looked at the same analysis for the new BGP free cores that all of our vendors are trying to convince us to move to?
Yes.
Same results?
Yeah, I mean, taking BGP off the boxes in the core does wonders, I think, in terms of just if you have a full table on it, for example, you know, it doesn't need to be there, and taking it off, I mean, it definitely helped in terms of CPU utilization. But I mean, how much, I'm not all that sure. I mean, it was nice to get, on this particular case, getting BGP off was nice, because having it on there, having full table routes and different, you know, when there was convergence, I recall there was some delays associated with it. I mean, I think overall it helped having BGP off the core boxes.
Thanks.
Richard Steenberg and Inlayer. One thing that you should add to the Juniper section is PPM delegate. If you have a modern architecture with distributed forwarding, T-Series, N320, MX, things like that, it will run your, like for example, your BFD or your other keep alive processes directly off the CPU of the line card instead of the routing engine, and that can help performance. Yeah, definitely. That was one thing I didn't think about was on the Junipers you can distribute the PPM process, which handles all the sub-second fast-related things, and I think it works pretty well for, you know, BFD. Although I think in some cases it actually has to run on the routing engine for like things like pseudo wires or link bundles where it can't be distributed. So. Okay, so that's it. I think it's going to be lunchtime now, and what is it? 2:30? Be back, or are you gonna?